this topic on Wednesday, but I need you to be focused today because we're actually going to make use of the knowledge of algebra and calculus. So we're going to use a combination of the board and, the lecture slide. I'm basically going to be going back and front. Now we started the function of random variable. I actually call this the real life application of the function of random variable. The real life is basically going to come from medical field, from physics and engineering, and from business. This actually cut across. We're going to talk about the discrete functions. We're going to talk about continuous functions. How some functions are derived from the existing probability function that could either be discrete or continuous. Now, I want to walk you through this example now. It's also in the lecture note for Wednesday. You have a discrete probability distribution. X follow discrete probability distribution, as you can see. And they ask you to find the probability distribution of a random variable y that is equal to S squared. The X itself is a random variable that follow a geometric distribution having a state space of 1, 2, 3, 4, and so on to infinity. Of course, we know what this distribution does. Of course, geometric distribution is actually the distribution that model, how many times am I going to fail before I record the first success? The X here actually represents the numbers of failures before you record the first success. Now, we are now seeking to we want to derive, when we know that X follow that distribution, we are seeking to get the probability of, when we square X, which is basically another random variable Y, which is equal to S squared. Now, what we're going to do, we are seeking to derive a probability function for Y, and it's a square of X. So what we're going to do, we need to first get the inverse. If Y equal to S squared, then you need to solve for X. When I solve for X, I'm basically going to have, I'm going to have two values. I'm going to have the square root of, plus square root of Y and negative square root of Y. Okay, the negative will be outside. But because of the fact that we know that the random variable X, if you take a look at the random variable X, it started from 1, 2, 3. There's nothing like negative. Okay, we don't need negative. We only need the square root of Y. Now, what am I going to do? If I want to solve the problem, wherever I see X in the distribution, I'm going to plug in square root of Y. When I plug in square root of Y, I already have a new distribution, which is basically going to be the distribution of Y, okay, when we square X, and X is a geometric variable. Now, then I'm going to also state the state space. When you take a look at the state space of X, what was 1, 2, 3. Now, I want to get the state space of Y, and don't forget that Y equal to S squared. Then it means I'm basically going to square the state space of S to be able to get the state space of Y. Any question? I'm done with that. Any question? The discrete one is very easy to do. Where we normally have difficulty is when we're dealing with a continuous one. Okay, now I'm going to go to the next one. Now, if you take a look at the one we did here, we're basically moving from X, from a random variable X to a random variable Y. That's a one-to-one. What if in a situation where we're talking about bivariate, where we got two variables, and the two variables now want to move to another set of new variables. I want to talk about 2 by 2. How am I going to do that? Okay, of course, I'm also going to find inverse function, except that I'm going to find my inverse function in two ways. In such a way, for instance, if y1 is a function of x1 and s2, and y2 is a function of x1 and s2 as well, then I need to find an inverse function. I need to solve for y1, for x1, I need to solve for x2. When I solve for x1 is going to be a function of y1 and y2. When I solve for x2, it's going to be a function of y1 and y2. Then what I'm just going to do is just to plug in into the joint of the distribution of the original function. Now I'm going to walk you through that now. Now, this is a very good example. Let x1 and s2 be two independent random variables having Poisson distributions with parameters mu1 and mu2 respectively. Find the distribution of the random variable y1 equal to x1 plus x2. Take a look at that. You want to find. Now, at this junction, I need you to focus on the board. At this junction, I need you to focus on the board. We got two, the first random variable x1. The x1 follow Poisson and x2 follow Poisson based on what you are given here with a probability distribution. Okay, so they told us x1 follow Poisson with parameter mu1. Okay, x2 follow Poisson with parameter mu2. Okay, then I'm basically going to write the f of x1. I have exponential raised to power mu1 raised to power x over x factorial. Yeah? Okay, then I also have f of x2 equal this raised to power mu2, or mu2 raised to power x2 divided by s2 factorial. Yeah? Okay, that's what I'm going to write first. Any question on this? Now, when you take a look at this guy now, okay, they wanted to find a random variable y, which is equal to x1 plus x2. Okay, don't forget the x1 follow Poisson, the x2 follow Poisson. This is like I want to move from two variables to one, but that's not possible. We can only move from 1 to 1 or 2 to 2 or 3 to 3. Then it means I'm actually going to create an artificial variable. Okay, maybe I create an artificial, like here now, we're creating artificial. If you take a look at that, we're assuming that, if this guy is actually y1, we are trying to create y2 is an artificial variable equal to one of these, equal to s2. Even though I don't need this guy, but in the end, okay, I'm actually going to integrate this guy out. It's just like maybe the first time I was given an appointment in the university to be a professor at the University of Minnesota. When I get to the University of Minnesota for the first time, I was trying to locate department of School of Statistics, and maybe I met somebody on the road and say, okay, how are you today? Sorry, can you direct me to School of Statistics? And the person is going to say, okay, when you go there, you're going to, that very person is more or less like a pointer, right? And in the end, I'm going to say, okay, thank you. It's like this person here. Okay. Now in the end, I'm going to, marginalize that. But why do I curate this guy? Because I cannot go from two variables to one. I can only go from two variables to two variables. Now, what am I going to have? So y1 equal to this, y2 equal to that. The very first thing you're basically going to do. The very first thing you're basically going to do is, x1 and x2, okay, they are independent. Can you see from the question? If they are independent, then you need to write f of x1, f of x2, okay? If they are independent, that's going to be called f of x2, Okay, so which means you're going to multiply this guy by this guy. You see that? When you multiply them, you're basically going to have that. Okay, you're going to have that where you can, you'll be able to combine this and this. You'll be able to, that's why you're going to have exponential, into mu1 plus mu2. Okay, and you're going to have mu1 raised to power x or mu2 raised to power x2 divided by x1 factorial, x2 factorial. So what you have now is a joint distribution for x1 and x2. Then the next thing you're going to do, you need the inverse. You need the inverse of x1. You need the inverse of x2. Okay. Now, when you create the inverse of x1 and x2, then we need the Jacobian. Okay. Now, from there, what we're now going to do is you get the inverse now. Okay. Like I said, okay. Y1, okay, is basically equal x1 plus x2, right? And y2 equal x2. Okay, we need inverses. Inverses. The first inverses, x2 equals x2 equal y2. Then I need x1. If you take a look at this one now, okay, I can do y1 equal x1. Instead of x2, I'm going to plug in y2. Then what is my x1 now? My x1 is y1 minus y2. This is the inverse of x1. That is for x2. What am I going to do now? Oh, what I'm going to do now, do you know the joint that I wrote the other time? Anywhere I see x1, I'm going to put this guy. Anywhere I see x2, I'm going to put this guy. Now take a look at that. That is how we, now when you now do that, which means the g of y1, y2 is basically the g of x2 into y2 comma x1 into y1 minus y2. That is what we mean. So which means we're plugging in y2 for x2, we're plugging in y1 minus y2 for x1 in the joint. You remember the joint that we just talk about, the joint that we have. Don't forget we got f of x1, x2 equal exponential raised to power mu1 plus mu2. Okay, and we basically have mu1 raised to power x1 mu2 raised to power x2, okay, divided by x1 factorial, x2 factorial. So which means what I'm trying to say in essence now, so if I basically want to get this guy, anywhere I see x1, I'm actually going to put y1 minus y2. Anywhere I see x2, I'm actually going to put y2. That is what led to gy1, gy2. Any question? That is what led to gy1, gy2 that you see here. Now, is that where I'm going? No. What am I interested in? I'm interested in the g of y1. Then I'm going to marginalize that. You know what you've done before, right? What you've done before when you have a joint distribution and you are interested in the marginal one, you are interested in the marginal distribution, then you're going to sum out over the range of the variable you are not interested in. So when I do that, take a look at that now. It means I want to get h of y1, but I'm interested in y1. Then I'm summing over the range of y2 that I'm not interested in. And that y2 will go from 0 to y1. Now in the end, you see what I got here. And when you take a look at what I got, okay, go ahead. Okay, how do we know what is the range of y2? That's a very good question. The range of y2 here is also going to be the range of s2. Why? Because y2 equal to s2. Good question. If I want to know the range of x1 now, if I want to know the range of y1 now, Okay, you look at the way the something is reading to be able to determine that. You have to determine the new range. That's a good question. Now, sorry. Now, what we get now, we actually get this guy. Finally, h of y1. Okay, give us exponential. You know, by the time you plug all that in, okay, you're basically going to see that initially, if you look at the first row, initially, there was no y1 factorial. But when you look at the second row, because I need that, I introduce y1 factorial here and the hub here, you know, they can cancel out. So why am I interested? Why do I need that? So that I will be able to rewrite the 1 factorial divided by y2 factorial into y1 minus y2 factorial as y combination y2. If I don't introduce y1 factorial, there's no way I will be able to do that. At times when we're deriving, we can introduce a no variable. But when you are introducing an unknown variable, you have to obey the rule of mathematics, because introducing y1 factorial divided by another y1 factorial is like I have introduced nothing, because the other one can cancel out the other one. Now, if you take a look at what I have now at the junction, you know, I got this guy divided by y1 factorial. Okay, then I got summation. Okay, y2 starts from 0 to y1. Then I got y1 combination y2, and I got mu1. Okay, y1 minus y2. Okay, and mu2. Okay, raised to power y2. Now, when you take a look at this guy here, we need the idea of binomial expansion. When I have it, from binomial expansion, okay, if I have a plus b raised to power n, what am I going to have? Okay, you know, if I have n combination 0, I'm going to have a raised to power 0, b raised to power 1. I'm going to keep going, right? You remember this? Okay, so this is going to be going, sorry. This is going to be n. This is going to be increasing. This is going to be going down. Do you understand what I mean? So this is going to be a1, okay, and this is going to be b, okay, raised to power n minus 1. I'm going to keep going until I get to n combination n, and a is going to carry n, b is going to carry 0. This is a binomial expansion. And when you take a look at this, if I want to write this guy in a general form, I'm basically going to say n combination high, a raised to power high, b raised to power n. I start from 0 to n. Look at that. The whole of this is more or less like, take a look at that. So I can go from here. If I can write this, if I can say a plus b raised to power n, if I can use that, the fact that a plus b raised to power n equal to this, then I can also generalize for this. Go ahead. You see one? Yeah, it's discrete variable. You know, Poisson is discrete. That's why we're using sum. Does that make sense? Okay, now that's a good question. Now, when you take a look at this now, if you take a look at what you have here, it's more or less like we're talking about the a plus b that we're talking about. What is our a? Our a now is looking like mu1, and our b is looking like a mu2. That is more or less like we're doing mu1 plus mu2, okay, raised to power y1. Look at that. And that was how, so when we now get to that junction now, okay, where we have that was how we got this. Any question? That was how we got the last one to be that. This is what we're looking for. Okay. Now we want to move to, the discrete one is kind of easy, but the difficult one is continuous. But the way I'm actually going to walk you through this, it's also going to look so easy. You get what I mean, right? Okay, now take a look at this question now. Um, let us be a continuous random variable with a probability distribution. You're given f of s equal to that. You have the range of s. This is continuous, right? Find the probability of the distribution, okay, of the random variable y equal to 2x minus 3. Now, how do I need to do the continuous one? If I want to do the continuous one, if you are given f of x and you are seeking to get f of y, the f of y you are seeking for is basically going to be you express x in terms of y multiplied by the determinant of Jacobian. And the Jacobian in this case, when you get the inverse x in terms of y, is basically going to be dx dy. Okay, now, and then I find the absolute value of that. Now, let us take a look at this question now. What is the inverse of 2y minus 3? It means you solve for x, right? When you solve for x, what do you get? Y plus 3 divided by 2. Okay, now you need the Jacobian of that. We use the Jacobian transformation when we're talking about continuous random variable. Now, I need the s dy. What is the s dy? The s dy is going to be 1 over 2. Okay, my Jacobian is 1 over 2. But if Jacobian is negative, that's why we need the absolute value. Absolute value, we convert that to positive. Okay, now in the end, you know what you're going to do? You're going to go back to the original function, the x divided by 12. Anywhere you see x, what are you plugging? You plug in the inverse. You plug in y plus 3 over 2. And after plugging the y plus 3 over 2, you're going to multiply by the determinant of Jacobi. Sorry, by the absolute value of Jacobian. So that is what you're doing here. The absolute value of Jacobian is 1 over 2. Then you multiply by that. Then we get a new function now. We get a new distribution now, which is y plus 3 over 48. But if you derive a new distribution, then you need state space for the new random variable. And how am I going to determine that? Then I will look at that. Y equal to 2x minus 3, right? What was the range of s initially? 1 to 5, right? So I need to look at the range of s to determine the range of y. Now, when I plug in, what is the lower end point in s? 1, right? Plug in 1. 2 times 1 minus 3. What is that? 2 minus 1, right? Then maybe the lower part of y will be negative 1. Now, what are you going to plug in now? Plug in the upper point in original distribution, which is 5. What is 2 times 5? 10. 10 minus 3 is 7. And that is why I was able to get the state space for the new variable in the derived distribution to be between -1 and 7. Any question? Do you know what I used to do when I was in college? If I want to know if I'm right, I will integrate the new distribution over the range of -1 to 7. The moment you give me 1, I will start celebrating that I get it right. Does that make sense? Are you also going to do the same, like checking your work? Because when you call something a probability distribution, the total area under a curve must be equal to 1. Any question before I move on? In fact, you're super good, right? Now, I want to go to another question, another one now. What if we're moving from 2 variables to 2 variables and we're dealing with a continuous? Do you know the only difference? We did a discrete one the other time, right? When S1 followed Poisson and S2 followed Poisson, you know what we did, right? But this time around, the X1 is continuous, the S2 is continuous. Then I need the idea of a Jacobian transformation is going to come in. But this time around, since I got 2 variables, my Jacobian will be 2 by 2 matrix. If I have 3 variables, my Jacobian will be 3 by 3. Now, if I have a 2 by 2 matrix in my Jacobian, if I want to determine the magnitude of my Jacobian, then I will find the determinant of the matrix. Okay, let's take a look at this example now. Let me see. Before this is just for one variable, but let me, before I go to two variables, let me look at another example for one variable for continuous. But this is a well-known fact in statistics. If a z, if I have a random variable that follow a standard normal distribution, that is z, follow normal distribution with mean of 0 and the variance 1. That's a standard normal distribution. When I square that, it will follow chi-square. You know, I stated the theorem the other time. This is the proof. If I want to make the proof now, y equal x minus mu. Now, if you take a look at what I have, if you take a look at this guy now, okay, y equal x minus mu over sigma or square. Don't forget, z is this. It's more or less like y is z squared. If I square standard normal variable, the distribution will give us chi-square with degree of freedom 1. That is what we want to prove here. Now, this is going to be 1 to 1. Now, in that situation, y equal to z squared. What would be the inverse? You saw for z, the z is going to be square root of, we're going to have a minus root y and minus, and a plus root y. You're going to get 2 of that. Okay, when you get 2 of that, okay, you differentiate, you get the Jacobian of this, Jacobian of that. Okay, Jacobian of this, Jacobian of that. And the Jacobian one is differentiating x with respect to, differentiating z, with respect to y. The Jacobian 1 is that, Jacobian 2 is that. The one Jacobian is negative. Don't forget, you're going to find the absolute value of that. Then you're now going to plug in, you're going to substitute for z squared in the function. Okay, now when you substitute for z squared, that's going to be y. Then you plug in the first Jacobian, you plug in the second Jacobian, you add them up. Look at that. When you add them up, since they are the same, you're basically going to have that guy, which is 1 over square root of 2 pi. Y raised to the power half minus 1 exponential raised to the power. Forgetting all this, I'm going to tell you. Look at what we have. What we have now is g of y, okay, equal 1 over square root of 2 pi, okay, y raised to the power half minus 1 exponential. This is a new distribution that is formed. How do we know whether this distribution is a chi-square or not? Okay, let's take a look at this. If I have a gamma with parameter alpha beta, I got, it's going to be f of y, okay, equal y raised to the power alpha minus 1 exponential raised to the power y over beta divided by this and this. From gamma, if we let, if alpha is v over 2, beta equal to 2, I'm going to have a new distribution, y raised to the power v over 2 minus 1, exponential raised to the power y over 2. I'm going to have gamma v over 2, then 2 raised to the power v over 2. What do we call this? This is a chi-square with v degree of freedom. You know that? If you compare this guy with this guy, okay, let's set v to be equal to 1 here and see whether you're going to have this. Now, when v equal to 1 means degree of freedom 1, right? Now, if I set v to 1, I'm actually going to have y raised to the power 1 over 2 minus 1 exponential raised to the power this. gamma 1 over 2, 2 raised to power 1 over 2. Now, what is 2 raised to power 1 over 2? That is square root of 2. What is gamma half? You know, gamma half from statistical theory is square root of pi. Please take notes. Gamma half is square root of pi. 2 raised to power half is square root of 2. Now let us now compare. It means here we are having square root of 2 pi. Oh my God. Take a look at that. Square root of 2 pi. This guy. Okay. Oh, sorry. There's 1 over 2 here. 2 here. This guy. What has happened? That's a chi-square distribution. This is a chi-square distribution with 1 degree of freedom. We've already proved that. Any question? Any question? Okay. Now, this is where we are going. This is where we are going. Now, I need it to be focused on, like I said, you can take a picture, okay? You can take a picture. Now, this is where we're going now. Take a look at what I have here now. Okay? Take a look at what I have here now. Okay? If both x and y are distributed independently following exponential distribution with mean parameter 1, find the distributions of A, u equal to x plus y, v equal to x divided by x plus y. If you want to do that, please, I need you to pay attention now. You know, let's first write this. X follow exp with parameter lambda. F of x will be 1 over beta x. You know that, right? Now, the same thing now, y also follow exponent, you know, also follow that. F of y, 1 over beta. I'm also going to have this, right? But we're told that the beta equal to 1. Do you see the question? The question actually said beta equal to 1. So if beta equal to 1, it means my f of x will be exponential. Because when I put 1, 1, then my f of y will be that. Does that make sense? When beta equal to 1. But what are we looking for? A said we want to find u, which is equal to x plus y. Okay? If we want to find u, which is equal to x plus y, we need another variable that we can create because we can't go from 2 to 1. Variable, we can't go from s and y to u. We can create an artificial variable. But let me tell you this. I will give an exercise today. When I have u equal to x plus y, okay, you know, if I can create another variable that is going to be this. Do you remember that look like a proportion? And I can create another variable. I can say v equal to x. V can be any of this. I'm still going to get the same result. So it doesn't matter what I use here because in the end, I'm still going to integrate it out. Does that make sense? It doesn't matter what I use here, but we got possibility. I can use v equal to x. I can use v equal to y. I can use what I'm using now. Now, what is the first thing I'm going to do? I need the joint because they said x and y are independent. The joint is going to be this, which is going to be this and this, which is this. That is the joint. And after getting the joint, I need the inverses. You know, if I want to get x here, s is going to be v. What is x plus y? U. You see that? S equal to that. If I want to get y, I can get my y from here. My y will be u minus, what is my x? VU. I can do y equal to u into 1 minus that. Now I got the inverse of x, the inverse of y. Look at that. Is there any question? What is the next thing I'm actually going to do? When I get the inverse of that and inverse of that, if I now want to get the f of VU, then I need to plug in x as a function. What am I going to plug in for x? VU. What am I going to plug in for y? U into 1 minus v. And after doing that, I will multiply by the determinant of Jacobian. I'm going to say that again. In my old joint, I'm going to plug in x is going to be VU, y is going to be this guy, then multiply by determinant of Jacobian. How am I going to get how am I going to set up my Jacobian? You know, my Jacobian is going to be this. Take a look at my Jacobian now. My Jacobian is going to be, if I come here, I need the x, the v, the x, the u. Then I come here, I need the y, the v, the y, the u. Please take a look at this. V, u, u. My Jacobian is going to be 2 by 2. Where I'm going to come here, what is the x, the v, u, the x, the u, v, the y, the v. Okay, when you come here, the y, the v minus u, the y, the u, 1 minus v, 1 minus v, then you find the determinant of a 2 by 2. The determinant of a Jacobian now is going to be u into 1 minus v minus, okay, uv. You know how we find the determinant of a matrix, or let me see, this multiplied by this minus, this is going to be a plus then, okay, because this times this is minus uv, another minus. So what am I going to have now? uv plus uv. This cancel out. My Jacobian is u. Let me first say this Jacobian here. Then when you find the absolute value, then you have that. So you got u. Okay. Now when you have u now, then when you plug in, then you're going to multiply that by u. So if you want to plug in now, what are you going to do? Where are we plugging in? You know, we have this guy, right? Now, you know what I'm trying to say now. You know, the f of xy, that was this guy, right? Okay, if I want to get my f of uv is now going to be, what is my x? Okay, what is the x plus y? X plus y, that is u, right? This is going to be u. What is the Jacobian? The Jacobian is u. Take a look at this. This is my joint. Now I need to look at the range. So what am I looking for initially? I'm looking for f of u. I'm going to integrate this with respect to v. Then I need to decide on the range for v. Okay, and don't forget the v is a ratio. Okay, v is a ratio. And the range is going to be from 0 to 1. 0 to 1. Okay, when you integrate this guy, you're going to have a constant, right? And when you have a constant, so my f of u is going to be, you know, integral this u dv from 0 to 1. So all these are constants. I'm basically going to have this v from 0 to 1. When you plug in that, your f of u will be this guy here. That's going to be your f of u. This is a gamma distribution. If you take a look at that, a gamma distribution with parameter 2 and 1. With parameter 2 and 1. if you want to know. If you have a gamma, that is u raised to the power alpha minus 1 exponential raised to power u over beta gamma gamma beta beta raised to power alpha. Okay, if you plug, I said this is parameter 2 1, which means alpha equal to 2, beta equal to 1. Okay, if you plug in 2 here, it's going to give you this. If you plug in, your beta is 1. If you plug in 1 here, it's going to give you this. What is the gamma of beta? Gamma 1 is 1, right? And 1 raised to power that. So, which means this is a gamma distribution with the parameter alpha equal to 2, beta equal to 1. Take a look at that. Oh, give me 1 second. Why is it not charging? Okay, it's charging now. Okay, does that make sense? Now, I quickly want to go into an application area. Business example. Oh, this will be super easy for you now. I don't even need to do anything here. This is easy one. A dealer profit in unit of $5,000 on a new automobile is given by y equal to s squared, where s is a random variable having a density function. Okay, find the probability density function of a random variable y. This is super easy. 1 to 1. What are you going to do here? You need to first find inverse of x, right? When you find the inverse of x, then what you're going to do next, okay, is the Jacobian. Okay, the Jacobian, which is going to be, you want to find the s, the y. When you find the y, when you find the s, the y, you find the absolute value of that. Then you plug in the values of x that you got, then you multiply it by the Jacobian, you're going to get the f of, you're going to get question A. Now, if you get question A wrong, question B will be wrong, because you want to use the probability density function you derive in question A to figure out that of that. Now, it said, using the density function of y, find the probability. You know what I'm going to do? I will write the answer. I will write the answer, and you can work it out. Okay, I'm actually going to provide the answer because of the time, but if you follow what we do, what we've done, you'll be able to know how to figure that out. Okay, now for A, the g of y is going to be y raised to power this minus 1, and the range is going to be that. This is for exercise 7.8. That will be the g of y if you follow what we've been doing. Now for B, you want to find the probability of y less than 500, and you have 5,000 in the question. You see 5,000? What is the ratio of 500 to that? That would be 1 over 10. Then it means you want to find the probability of y less than 0.1, which means 0.1. Oh, sorry. Which means it's 0 to 0.1. Then you need to integrate this, the y. Your final answer, if you get it right, your final answer is going to be 0.5324. Please try that. This is example in business. The same approach go to the example in medical field. In medical field, okay, it is not only doctors that work in hospital. There's a lot of people that are, professionals. Okay, take a look at the FFS. Is the hospital period in days for patients following treatment for a certain type of kidney disorder is a random variable y, which is equal to s plus 4. Where s is given, that's a probability. Now you want to find what is the probability density function for y when y equal to s plus 4. When you figure this out, I'm going to write the answer again. You can confirm that if you get it right. Okay, for medical one now, 7.9. Okay, the G of y is 32. That where y greater than 4, and B, the probability of y greater than 8. Okay, your final answer is going to be 1/4. You can check that if you get it right. Okay, you can check that. The last question for the day: application in physics and engineering. But let me tell you, in this one, you basically need to set up a Jacobian matrix of 2 by 2. Why? The current of I amperes flowing through a resistance of R ohms varies according to the probability distribution. I is from 0 to 1. If the resistance varies independently of the current according to the probability distribution, take a look at that. The current is a random variable. Resistance is also a random variable, but they are independent. Find the probability distribution of the power, W. Power equal to I square R. Power is, multiplying the square of, the current with the resistance. So which means here you need to create an artificial variable. Okay, so that artificial variable that you're going to create, equate it to resistance. Okay, now if you want to approach this question, you're going to multiply f of I by f of g of r. You're going to joint, then you get the inverses of this, then you set off the Jacobian, you get the Jacobian, then the moment you get the joint, then you can, you're actually going to have a g of w. Let me give you the answer. If you do it right, I'm going to give you the answer now. You can just try and check that out. Okay, we have less than 1 minute. In fact, our time is up. Okay, now you set that one to this, you set this to that. Okay, so when you do that, your g of wv will be 6 into 1 minus square root of w over v. Your h of w will be 6 plus 6w minus 12. That, okay, this is what you're going to get at the end of the day, where the w will lie between 0 and 1. Don't forget, you are actually curating this guy. That was why you're going to get GVW. That's why you're going to get GW. Okay, and don't forget, when you are starting, you need to first get f of I R, which is going to be f of I multiplied by g of R, right? You're going to get a joint from here. Okay, and you're going to find the inverse from there. Okay, that's where I'm going to stop today. Any question? Please make sure you do the exercise. Okay, make sure you do the exercise and see whether you get it right. Okay, this is where I'm actually going to stop today. Make sure you stay safe and have a lovely day. Bye for now, everyone.